In this video, we're going to go over a few static equilibrium problems. Now, there are two things that you need to know. The net force must be zero. The sum of all forces in the x and y direction must be equal to zero. So you have translational equilibrium. Now, you must also have rotational equilibrium. So the sum of all the torques must be equal to zero as well. So when these two conditions are met, then static equilibrium will occur. Now let's review torques. Let's say if you have an object that can rotate about this pivot point, and if we apply a force at an angle, and let's say this is the length of the bar, so to speak, then the torque is the cross product of R and F, which is F times R sine theta, where theta is the angle between R and F. So we're going to use this formula a lot to calculate the torque in these problems. In addition, we need to talk about the sign conventions that we're going to use for our torque calculations. Let's say if we have two forces, F1 and F2. F2 will create a counterclockwise rotation, so it's going to create a positive torque. F1 will create a clockwise rotation, so it's going to create a negative torque. Let's try this problem. A 40-kilogram child sits on a seesaw 3 meters away from the pivot point. The mass of the bar is 10 kilograms. Where should a 30-kilogram child sit to balance the seesaw? So let's begin by drawing a free body diagram. So here's the pivot point, or the fulcrum, and here's the first child. Let's just draw a stick figure. Now the weight force exerted by the first child, let's call it F1. And this child is 3 meters away from the pivot point. Now the second child is X meters away from the pivot point. That's what we're looking for. And this child will exert a weight force that we're going to call F2. Now, the mass of the bar also exerts a weight force, and the pivot point exerts an upward normal force, which supports the other three downward forces. So we can calculate the normal force first, or the location where the 30-kilogram child sits. It doesn't matter what order we do it. So let's start with the normal force. So we know that the sum of all forces in the y direction must be equal to zero if we are to have static equilibrium. Now the normal force is an upward force, and the other three forces are downward forces. So we're going to put a negative sign in front of it. Now if we add the three forces with a negative sign and move it to the left side of the equation, we can see that F1 plus F2 plus the weight force of the bar is equal to the normal force exerted by the pivot point. So the weight force of the first child is simply mg. It's 40 kilograms times 9.8. The weight force of the second child is 30 kilograms times 9.8. And the weight force of the bar, the mass of the bar is 10 kilograms, so it's going to be 10 times 9.8. And this should equal the normal force exerted by the pivot point. So because each term has a common number, 9.8, we can add 40, 30, and 10, which is 80. So it's 80 times 9.8. and therefore the normal force exerted by the pivot point is 784 newtons. Now that we have the normal force, let's calculate the location where the 30 kilogram child should sit. So now we need to analyze the torques created in this situation. So let's choose the center of rotation as the pivot point. So therefore, the normal force and the weight force will not create a torque because they're located at the pivot point. Their R value is 0. Torque is F times R. So if you're directly on the pivot point, that force will not create any torque. So there's going to be two torques created. T1, which is a counterclockwise torque, that's positive. And T2, that's a clockwise torque, so that's going to be negative. So we know that the sum of the torques must add up to 0. So that's T1 minus T2. If we add T2 to the other side, we can see that T2 is equal to T1. T2 is F2 times R2, that's X times F2. And torque 1 is F1 times R1. F2 is M2G. F1 is M1G. So if we divide both sides by G, we can get rid of gravitational acceleration. So the mass of the second child is 30 kilograms times X, and the mass of the first child is 40 kilograms times R1, which is 3. So let's divide both sides by 30. So 30 over 40, we can cancel a 0. That's basically 4 over 3. So it's 4 times 3 divided by 3, which we can cancel a 3. So therefore X is equal to 4. So to balance the seesaw, the 30 kilogram child needs to sit 4 meters away from the pivot point. Here's another problem. So let's say if this is the wall and here's the ceiling, and if we have a hanging sign supported by 2 ropes. And let's say the mass of the sign is 50 kilograms. Now let's call this force T1 and the tension in the other cable T2. How can we calculate T1 and T2? What would you do? And let's say this is the weight force mg. Well, let's write the equations that we have. T1 has an x component and a y component. And there's one thing I'm forgetting, and that's the angle. Let's say this angle between T1 and the ceiling is 60 degrees. So that would mean this is 60. These are alternate interior angles, and they're congruent. So this is 60 as well. So the sum of the forces in the y direction must equal 0, which means that T1y minus mg has to equal 0. Therefore, we can say that T1y is equal to mg. Now, what about the forces in the x direction? These two must add to 0. So we have T1x and T2. So T1x is directed towards the right, so we're going to put a positive sign in front of it. and T2 is directed towards the left, so it's negative. So if we add T2 to both sides, we can see that T2 is equal to T1x. Now, it turns out that we don't really need to use torques to solve for T2 and T1 in this equation. But we know that for this to remain still, the net torque must be 0. Now we can calculate T1y because we know the mass. T1y is equal to mg, and that's 50 kilograms times a gravitational acceleration of 9.8. By the way, for these problems, make sure you always draw a free body diagram. It helps when you can see all the forces. So 50 times 9.8, this is 490. So that's T1y. Now, if we have the value of T1y, we can calculate T. Now, according to SOHCAHTOA, SOH, sine theta is equal to the opposite side, T1y, divided by the hypotenuse, T. So if you rearrange that equation to solve for T1y, T1y is T sine theta, or T sine 60. So to solve for T, it's going to be 490 divided by sine 60. And make sure your calculator is in degree mode. So the tension force is about 565.8 newtons. And this is, of course, T1. So now that we have the value of T1, we can calculate T2 by finding T1x. So let's go ahead and do that. Let's move this somewhere else. So T2, which equals T1x, and T1x is T1 cosine theta, or T1 cosine 60. So this is simply going to be T1, which is 565.8 times cosine of 60 degrees. And so the tension force in the other cable is 282.9 newtons. And that's all you got to do for this problem. Now let's try another problem similar to the last problem. This time we have a hanging mass that has a mass of 80 kilograms, and we have two cables. We want to calculate T1 and T2. So what can we do to solve for the two tension forces? So we need to draw a free body diagram. T1 has an x component, which we'll call T1x, and it has a y component, T1y. Now, if this angle is 40, then this angle must also be 40 as well. Now, T2 has an x component and a y component, T2x and T2y, and this angle is also 50. And then we have the weight force mg. So the sum of the forces in the x direction must be balanced. Therefore, there's only two forces in the x direction, and those two forces must equal each other. They have the same magnitude, but they're opposite in direction. So T1x is equal to T2x. Now, the sum of the forces in the y direction must also add to 0. So T2y and T1y has to support the weight force mg. So we could say that T1y plus T2y equals mg. So we have two equations and two variables, T2 and T1. How can we use these two equations to solve for these two variables? So we need to use substitution to get the answer. So let's start with this equation. T1x is T1 cosine theta. And the angle associated with T1 is 40. T2x is T2 cosine 50. So let's solve for T2. So T2 is going to be T1 cosine 40 divided by cosine 50. And cosine 40 over cosine 50 is about 1.1918. So 1.1918 T1 is equal to T2. Now let's save that equation. So I'm going to write it here. Now let's work with the second equation. T1y is T1 sine theta. So that's T1 sine 40. T2y is T2 sine 50. And mg is basically 80 times 9.8, which is equal to 784. Now let's replace T2 with 1.1918 T1. Now let's simplify the expressions that we now have. Let's convert everything into decimal values. Sine 40 is about 0.6428 times T1. 1.1918 times sine 50 is equal to 0.913 or 297, which we can round into a 3, T1, and that's equal to 784. So at this point we can combine like terms. But before we do that, let's make space. So 0.91297 plus 0.6428, if you add those two, this is going to be 1.5558 T1, and that's equal to 784. So to solve for T1, let's divide 784 by 1.5558. So T1 is equal to 503.9 newtons. So now that we have the value of T1, we can calculate T2 using this equation. So T2 is simply 503.9 times 1.1918. And you should get about 600.5 newtons. So that's T2 and T1. Let's try another problem. So let's say if we have a uniform beam, that's this object right here, and let's say it has a mass of 100 kilograms. And on top of it we have a 20 kilogram box, and let's say that the length of the beam is about 10 meters. And the box is located 8 meters from the left vertical support column, which is this part right here. What are the forces exerted by each support column? So what is the value of F1 and the value of F2? What can we do to calculate these two forces? Go ahead and try this problem. So the weight of the beam is located at the center of gravity. So that's going to be 5 meters from the first vertical column, and from the other one too. And then we have the weight of the box, which we'll call mg. So let's write an equation for all of the forces in the y direction. So the sum of all forces in the y direction, it's going to be F1 plus F2. These are upward forces minus the downward forces, mg for the beam and mg for the box. Now we know that the forces in the y direction must add up to 0 if this situation is to be in static equilibrium. mg is going to be the mass of the beam, which is 100, times g, which is 9.8, so that's 980. And the other mg is 20 times 9.8, so that's 196. So let's go ahead and replace these values. So this is 980 newtons, and this is 196. So if we add these two and then move it to the other side, we could see that F1 plus F2 is equal to 980 plus 196, or 1176 newtons. So at this point, we only have one equation, but we have two variables. So to solve those two variables, we need another equation. So we need to use torque. So we need to choose an axis of rotation. We can choose the left support column or the right support column, because it can cancel either F1 or F2. It really doesn't matter which column we choose. In both ways will give you the same answer. But let's choose the left support column. So if this is the axis of rotation, F1 will create no torque. Now, F2 will create a counterclockwise torque, so it's going to be positive. Let's call the torque created by F2 T2, and the torque created by the box, let's call it T1. And because it's moving in a clockwise direction, that torque will be negative. And the torque created by the mass of the beam is also negative. Let's call it, we'll call this one, let's say T1 and T3. So the sum of all torques is going to be T2, which is positive, created by F2, minus T1, which is created by the beam, minus T3, which is the clockwise torque created by the mass of the box. So all of these torques must add up to 0. T2 is going to be F2 times the moment arm, which is the distance between F2 and the axis of rotation. So F2 is about 10 meters away from the axis of rotation. T1, the torque created by the mass of the beam, it's about 5 meters from the axis of rotation. So this is going to be 980, that's the weight of the beam, times 5. T3, the weight of the box, is 196, and it's 8 meters from the axis of rotation. (980) times 5 is 4,900, and 196 times 8 is 1568. If we add those two, we should get 6468. So 10 times F2 minus 6468 is equal to 0. So 10F2 is equal to 6468, and if we divide by 10, F2 is going to be 646.8 newtons. So now that we have the value for F2, we could solve for F1. So F1 plus F2, or 646.8, is equal to 1176. So F1 is simply 1176 minus 646.8. And that's going to be 529.2 newtons. Now in this problem, we have a hanging mass of 200 kilograms, and the mass of the beam, let's say it's 30 kilograms, and the angle that the tension or the cable makes with the beam, let's say this is 30 degrees, and this is the tension force T. And here is the hinge, which I forgot to draw. Let's put it there. And so this is going to be the axis of rotation. Let's say the distance between the hinge and the hanging sign, let's say this is about 2.2, actually just 2 meters. So with this information, go ahead and calculate the tension force and also the components of the forces that the hinge exerts on the beam. So the hinge is going to exert a y component, which is, we'll call it FHY, and it's going to exert a force in the x direction, which we'll call FHX. So feel free to pause the video and try this example. Now we need to realize that the tension force has a y component, which we'll call Ty, and it has an x component, which we can call Tx. So the only forces that are acting in the x direction is FHX and Tx. So these two forces are equal to each other. So Tx is equal to FHX. So we can't do anything with this equation right now. So now let's look at the forces in the y direction. We have Ty, FHY. We also have the weight of the sign, which we'll call mg, and the weight of the beam, which we'll call capital mg. So the two upward forces, Ty and FHY, they have to support the downward forces, that is the weight of the beam and the weight of the hanging sign. So the weight of the beam is going to be 30 times 9.8, which is 294. And the weight of the sign is 200 times 9.8, which is 1960. If you add 1960 and 294, this is going to be 2254 newtons. So that's equal to Ty plus FHY. Right now we have two equations and 4 different variables, so we need more information. So now let's analyze the torques in this problem. Ty is going to create a torque in the counterclockwise direction, so that torque is going to be positive, and let's call it T1. Mg is going to create a torque in the clockwise direction, so that torque is going to be negative. Let's call it T2. And the weight of the beam will also create a torque, T3. Now, if we choose the hinge as the axis of rotation, then these forces will create no torque because the R value will be 0. So therefore, we can write an equation for the sum of all torques. It's going to be T1, which is positive, minus torque 2 and torque 3. Now the net torque has to add up to 0. And T1 is basically Ty times the length of the beam, which is 2 meters. And Ty is T sine theta. And the angle is 30, so it's sine 30 times 2. And then minus T2, which has a weight force of 200 times 9.8, and that's 1960, times an R value, or moment arm, of 2. And then minus T3, which has a weight force of 30 times 9.8, which is 294. And it's at the center of gravity, so it's half of 2. So that's 1. So it's 294 times 1. Sine 30 is 1/2, and 1/2 times 2 is 1. So this is simply T. 1960 times 2 is 3920. And if we add 294 and 3920, we're going to get 4214. So that's the tension force T. Now that we have the value of T, we can calculate everything else that we need. So let's find the X component of the force that the hinge exerts on the beam. So let's calculate FHX, which is equal to TX. And TX is T cosine theta, and T is 4214, and then times cosine 30. So this is equal to 3649.4 newtons. So that's the X component of the force exerted by the hinge. Now to find the Y component, we need to use the second equation, which is this one. So Ty is going to be T sine theta plus FHY, and that's equal to 2254. Now T is 4214 times sine 30 plus the other stuff. Sine 30 is a half, and half of 4214 is basically 2107. Half of 42 is 21, half of 14 is 7. So therefore, f of hy is 2254 minus 2107, which is 147 newtons. So that is it for this problem. So here we have another hanging sign problem. The mass of the sign is 15 kilograms. We have a tension force, T, by means of the cable, and it forms an angle of 30 degrees with the beam. Now the length of the beam, that's about 10 meters. And the mass of the beam is 20 kilograms. And this distance is about, let's say, 4 meters between where the tension force connects with the pole and the hinge, or the pivot point. So with this information, go ahead and find the tension force and the X and Y components of the force that the hinge exerts on a beam. So that's FHX, and FHY. So let's go ahead and solve it. So let's look at the forces in the X direction. The tension force is completely horizontal. So this is the same as TX. It has to be equal to FHX. Those are the only two forces acting in the X direction. Now in the Y direction, we have an upward force exerted by the hinge, FHY, and that supports the weight of the beam and the weight of the hanging sign. So we could say that FHY is equal to mg, that's the weight of the beam, which is basically 20 times 9.8, which is 196, plus mg, the weight of the sign, which is 15 times 9.8, and that's 147. So if we add these two numbers, we could see that FHY is equal to 343 newtons. So we need to find T and FHX. Once we find one of them, then that's it. We're done with this problem. Now let's consider the torques acting on the system. Our axis of rotation is going to be the pivot point. So FHY and FHX will not create a tension or a torque around the pivot point. Now, the tension force will create a positive counterclockwise torque, which we'll call T1. The 15 kilogram sine will create a torque that's negative, which we'll call T2, and the 20 kilogram beam will create a negative torque called T3. So the sum of torques, the sum of all the torques, it's going to be positive T1 minus T2 minus T3. So now, how can we find T1? It turns out that torque 1 is simply the tension force times 4. 4 is the moment arm. Now, for those of you who are unsure about that, we know that if you have an object that can rotate, if you apply a force, then the perpendicular distance between where you apply the force and the line of action of the force, this is called the moment arm, that perpendicular distance, and the torque is simply the product of the force and the moment arm. Now, if you apply it at an angle, let's say if you apply the force here, then the torque is simply Fr sine theta. But let's understand why that's the case. When you apply a force at that point, this is the line of action of the force. And the perpendicular distance between the line of action of the force and the axis of rotation is this distance right here. And according to SOHCAHTOA, sine theta is equal to the opposite side, which is the moment arm, divided by the hypotenuse of the triangle, which is across the 90-degree angle, and so that's r. So if you solve for the moment arm, you'll see that it's r sine theta, which gives you the same equation. So the torque is F times the moment arm, which is the perpendicular distance between the line of action and the axis of rotation. So therefore, for our particular example, T1, the torque created by the tension force, is simply going to be the tension force, and this is the line of action. So 4 is the moment arm, that's the distance between the line of action and the axis of rotation. So torque 1 is simply T times 4. Now, if you prefer to do it the other way, using the equation Fr sine theta, you're going to get the same result, but there's more work involved. So let's do it the other way, and so you can see why it's T times 4. So this is going to be the tension force times the distance between the axis of rotation and where you apply the tension force, which is the hypotenuse of that triangle, times sine theta. Let's call that distance L. So notice that L is not 10, it's less than 10. 10 is the length of the entire beam, but we're trying to find L, the distance between where the tension force acts and the axis of rotation. So let's focus on this particular triangle. Now let's redraw it. So we have a 30-degree angle. This is the right angle. This is 4, and we're looking for L. So according to SOHCAHTOA, sine theta, or sine of 30, is equal to the side opposite to it, which is 4, divided by the hypotenuse, which is across the box. And so that's L. Now, if we rearrange the equation, or if we cross multiply, 1 times 4 is 4 times L sine 30. So solving for L, it's going to be 4 divided by sine 30. Now keep in mind this angle is also equivalent to sine 30. So now let's plug in L into the equation. So it's going to be T times L, which is 4 over sine 30 times sine 30. So as you can see, these angles will cancel and it's simply going to be T times 4. So regardless of which method you choose to use, that's going to be the tension force, the torque created by the tension force. It's just 4 times T. So now let's move on to T2 and T3. So T2 is created by the 15 kilogram mass. So it's the weight force, which is 15 times 9.8, which we already know it to be 147, times L, or the length of the beam, but this is the entire beam, which is 10 meters, and times sine theta. But now what angle should we use? Now let's focus on the 30-degree angle. So here's the tension force, here's the beam, and there's a weight force. So the angle between the weight force and the length of the beam, which you can call it R or L, is this angle, which is 60 degrees. And even if you analyze another force, this is going to be 30 and this is going to be 60 as well, just based on the rules of geometry. So knowing that, that means that this angle here is 60 degrees and this angle is also 60 as well. So let's multiply 147 and 10 by sine 60. And then minus T3, which is the weight force created by the 20 kilogram mass. So 20 times 9.8 is 196. And it's at the center of gravity, so it's located at the center of the beam, which is half of 10, and that's 5 meters. And it creates an angle of 60 degrees between itself and the beam, so that's sine 60. Now what we need to do is make some space. So let's get rid of most of this stuff. So what we now have is 0 is equal to 4t, and 147 times 10 is 1470 times sine 60, and that's negative 1273, minus 196 times 5, which is 980, times sine 60, and that's going to be 848.7. 1273 plus 848.7, that's 2221.7. It's negative on the right side, but if you move it to the left side, it's going to be positive. And that's equal to 14. So now let's divide both sides by 4. So the tension force is 530.4 newtons. Now keep in mind the tension force is also equal to the x component of the force exerted by the hinge or the pivot point. So FHX is also 530.4 newtons. So that is it for this problem. So here's another problem. At this time we have a ladder leaning against a wall, and the length of the ladder is 10 meters. And the mass of the ladder, we're going to say it's 8 kilograms. Calculate all the forces that are acting on the ladder. So you want to find the force exerted by the wall. Let's call it FW. And the force exerted by the ground, FGX. and also FGY. Now, this distance here is 8 meters. Feel free to pause the video and work out this problem. So let's analyze the forces in the y direction. We have FGY and the weight force mg. So therefore we could say that FGY has to be equal to mg. So that's 8 times 9.8, which is about 78.4 newtons. Now notice that the forces in the x direction are FGX and FW. So the force exerted by the ground in the horizontal direction, FGX, is equal to the force exerted by the wall on the ladder, FW. Now we need to use torques to solve this particular problem. So we're going to say this is the axis of rotation, so we can eliminate FGY and FGX from the torque expression. And so there's going to be two torques that we need to be concerned with. That's the torque created by FW. That's going to be a positive torque. We'll call it T1. And the 8 kilogram mass will create a negative torque, T2. So the sum of all torques is simply T1 minus T2. And that needs to equal 0. T1 is the product of the force exerted by the wall and the lever arm. To easily find the lever arm, extend the line of action of FW and draw a parallel line that passes through the pivot point, or the axis of rotation. The distance between these two lines is the moment arm, which is 8. So that's a simple way to find the moment arm. So it's going to be FW times 8. Now, T2, if you notice, it's created by the 8 kilogram, it's created by the weight force of the 8 kilogram object. And if we draw a parallel line that passes through the axis of rotation, the distance between these 2 points is the moment arm for the 8 kilogram mass. So this is going to be mg, which is 8 times 9.8, that's 78.4, times whatever this distance is. Now let's go back into geometry, or trigonometry. You need to know special triangles, such as the 3, 4, 5 triangle. According to the Pythagorean theorem, a squared plus b squared equals c squared. 3 squared plus 4 squared equals 5 squared. 3 squared is 9, 4 squared is 16, 9 and 16 is 25, which is 5 squared. Now, you can also use a similar ratio. Instead of the 3, 4, 5 triangle, you can use the 6, 8, 10 triangle. Notice that the hypotenuse is 10, this side is 8, so the missing side must be 6. So this distance here is 6 meters, which means the distance that we want between the two lines, the two yellow lines, must be 3 meters. It's half of 6. So torque 2 is going to be the weight force of the ladder, which is 78.4, times the moment arm of 3. So FW is going to be 78.4 times 3, which is 235.2. If you move it to the left side, it's positive 235.2 divided by 8. So FW is equal to 29.4 newtons. Now, for those of you who like to get the same answer, but using the other method, here's what you can do. So let's get rid of this for now. So let's say if you simply want to use the distance of the beam. If you're going to do it that way, you need to find the angle between the force and the length of the beam. So let's say the length of the beam is L. T1, the torque created by Fw is going to be F times L times sine of theta, where theta is the angle between the length of the beam and Fw. So if that's theta, this is theta according to the alternate interior angle theorem. So there must be this other angle. I believe that's called phi, if I remember correctly. So if you extend the weight force of the 8 kilogram mass, this angle is also phi. So for T2, it's going to be the weight force, mg, which is 78.4, times the length of the beam, times the angle between the weight force, which is right here, and the beam, which is phi. So that's going to be sine of that angle. Now let's draw a triangle. So here's theta, here's the other angle. The hypotenuse is 10, this side is 8, and we know this side is 6. So it's Fw times L, where L is 10, times sine theta. Now, based on this triangle, sine theta is equal to the opposite side divided by the hypotenuse, which is 8 over 10. So as you can see, 10 cancels, and it's just going to be Fw times 8, which we had before, minus 78.4. Now this is really supposed to be L over 2, because the 8 kilogram weight force is at half of the beam. It's not at this point where the length is 10, it's at the middle, so it's really L over 2. So 10 over 2, which is 5. And sine of the other angle is going to be opposite, which is 6, divided by the hypotenuse, which is 10. So this is 6 over 10. 5 times 6 is 30, and 30 divided by 10 is 3. So we get the same equation, Fw times 8 minus 78.4 times 3. And as we know, 78.4 times 3 divided by 8 will give us the same force of 29.4 newtons. So you want to learn how to do it the easy way, and that is finding the moment arm that is perpendicular to the line of action, and it's the distance between the axis of rotation and line of action. So now that we have Fgx, Fw, and Fgy, let's calculate the force that the ground exerts on the ladder. That is the resultant force, Fg. So Fgx is horizontal, Fgy is vertical. So Fg, the resultant vector, is the hypotenuse of this triangle. And let's also calculate the angle that it makes with the ground. So according to the Pythagorean theorem, we know that c squared is a squared plus b squared, which means the hypotenuse c is the square root of a squared plus b squared. So the hypotenuse f of g must be the square root of f of gx squared plus fgy squared. So that's going to be the square root of 29.4 squared plus 78.4 squared. So the resultant force vector is 83.7 newtons. So now that we have that value, we can calculate the angle. So according to SOHCAHTOA, TOA, tangent theta is equal to the opposite side divided by the hypotenuse. So theta is the inverse tangent of Fgy divided by Fgx. So that's the inverse tangent FGY is 78.4. FGX is 29.4. And so the angle theta is 69.4 degrees. So this is going to be the last problem for today. This time, we're going to have a person standing on the ladder. Now the mass of the ladder is going to be, let's say, 10 kilograms. Maybe I should put that on top. And the mass of the person is going to be 70 kilograms. Now the length of the ladder, we're going to say it's 15 meters. And we're going to say this distance is 9 meters. Now let's say that the ladder and the wall, there's no friction between the ladder and the wall. But at this position where the person is located, the ladder begins to slide at its base. And our goal is to find the coefficient of static friction in this problem when the ladder begins to slide. Now, we also know the length of the base, how far the base of the ladder is from the wall. And let's say this distance is 12 meters. And let's say that the person is located 8 meters from the foot of the ladder. Now, with this information, you can calculate the coefficient of static friction between the ladder and the floor or the ground. So let's begin. Let's label the forces that we have. So we have the force exerted by the wall on the ladder, and since this force is perpendicular to the wall, it's by definition a normal force. Now we also have the force of the ground, FGY, and also FGX. Now, let's say if we have a box on a surface. If we apply a force, we know that static friction will resist the applied force to keep the box steady. And there's also the normal force exerted by the ground on the box. So notice that the normal force exerted by the ground is the same as FGY. And the static frictional force is the same as FGX. So in this problem, you want to understand that FGY is the normal force exerted by the ground on the ladder, and FGX is the static frictional force. Now we know that static friction is equal to mu s times normal force. So the coefficient of static friction is static friction divided by the normal force. And static friction is FGX, and the normal force is FGY. So if we could find FGX and FGY, we could find the coefficient of static friction. We simply need to divide the two. So let's begin with the forces in the x direction. So we know that FGX has to equal FW because those are the only forces in the x direction. And FGY has to support the weight of the ladder and the weight of the person. So FGY is going to equal mg, the weight of the ladder, and mg the weight of the person. Now the weight of the ladder is simply 10 times 9.8, which is 98 newtons. And the weight of the person is 70 times 9.8, which is 686 newtons. So therefore, FGY, which is 98 plus 686, that's 784 newtons. So let's conserve space. Let's get rid of this stuff, and let's move this here. Now let's consider the torques in this problem. So the sum of all the torques is equal to, so we have T1 created by the force of the wall, and that's in the counterclockwise direction. So that's going to be positive. T2 created by the weight of the person, that's negative. And T3 created by the weight of the beam or the ladder, and that's negative. So we're going to find the torques using the easy method, that is finding the moment arm that is perpendicular to the line of action. So let's start with T1. The sum of all the torques is going to be 0. So to find the moment arm the easy way, draw the line of action of the force that creates torque 1, which is Fw, and draw a line that's parallel to that line but passes through the pivot point. The distance between those two lines is the moment arm. So the moment arm for Fw is 9. So T1 is going to be Fw times 9. Now let's work with T2. So torque 2 is created by the weight of the person. And so this is the line of action for the weight force. Let's draw a parallel line that passes through the pivot point, and the distance between these two lines is 8 meters. So that's the moment arm. So T2 is going to be the weight force of the 70 kilogram mass, which is 70 times 9.8, and that's 686 times the moment arm of 8. Now T3, the weight force for T3 is the 10 kilogram mass times 9.8, which is 98. And to find the moment arm, draw a line parallel, that is the line of action, which is parallel to the weight force of the ladder. And let's draw a line parallel that passes through the pivot point. And so the distance between these two lines is the moment arm. So if this distance is 12, and we know that the weight of the ladder is right in the middle at the center of gravity, this must be 6, half of 12. So it's going to be 98 times 6. 686 times 6, 686 times 8, that's 5488. And 98 times 6 is 588. So if we add 5488 plus 588 and move it to the other side, it's going to be 6076 is equal to 9 times Fw. So if we divide both sides by 9, the force exerted by the wall is 675.1 newtons. Now remember, Fw is the same as Fgx. So Fgx is equal to 675.1 newtons. Now that we have Fgx and Fgy, we can calculate the coefficient of static friction. And so that's Fgx, which is 675.1, divided by Fgy, which is 784. So this is equal to 0.861. So this is the coefficient of static friction. So that is it for this video. Thanks for watching and have a great day.